Dear students, today we'll see some numerical examples on diode. So our topic will be simple problems on diode circuits. And let's go with example number one. Now in this example number one, we will solve it like it is an ideal diode. Okay, we will not take the practical considerations. We'll solve it as the ideal diode as it is our example number one. So example number one is saying find the total current IT in the circuit. Okay, now in this circuit, if you see the applied voltage is 5 volt. Okay, and the resistance which is there is 1 kilo ohm. 1 kilo ohm is nothing but 1000 ohms. And then you are having a diode here, D1, diode D1. So if you see the placement of the battery, the positive terminal of the battery is connected to anode of the diode. So anode of the diode is connected to positive terminal of the battery and negative terminal of the battery is connected to cathode. That means the anode is more positive than cathode and the diode is in forward bias condition. That means it is going to allow current to flow, and for an ideal diode we will take this voltage across it as 0 volt, because ideal diode we are not going to consider the knee voltage. Okay, that is the potential barrier voltage of the diode. So we will take it as an ideal diode, and ideal diode we will take it as short circuit and 0 volt. Okay, now here since D1 is forward bias, it is going to act as short circuit. Therefore, the voltage across diode will be 0 volt as shown here. And then the voltage, the main voltage which is applied to the circuit is 5 volt. Okay. So here you can see voltage across diode is 0 volt and the main voltage is 5 volt. Now to find the current, the formula will be a current is equal to voltage upon resistance according to our Ohm's law. Okay, so here then what is the total voltage? So if you are taking, if you are not considering the practical cut-in voltage of D1, or which is called as potential barrier, then if that voltage is 0, then you can take VRN1 as 5 volt only. Voltage will be as 5 volt and resistance is around 1 kilo ohm, that is 1000 ohms. So it is 5 volt upon 1000 ohms, which will give you 5 milliampere. Therefore, the current which is flowing through the circuit, that is this current IT will be equal to 5 milliamperes. Now here we have taken diode as an ideal diode. In our next example, a same type of circuit we will see, and we will take the diode as a practical diode, and in that we will see the potential barrier of that silicon diode. Okay. Now here in this example also find the current IT in the circuit is given. Okay. So here also we see that the applied voltage is 5 volt and then the resistance is 1 kilo ohm, that is equal to 1000 ohms, and the diode is forward biased. The diode is forward biased. Okay, now when the diode is forward biased, in our last example we took the voltage across it as 0, but actually practically the applied voltage has to overcome the potential barrier. So when it is forward biased, the voltage will be 0.7 volt for silicon diodes. Okay, so that now we will take it as a practical or diode and will take voltage as 0.7 volt. So here diode is forward biased, it acts as a short circuit and the voltage across the diode is 0.7 volt. Therefore the total voltage will be how much? 5 volt minus the potential barrier, 5 volt minus 0.7 volt, 5 volt minus the opposing force or opposing voltage. So 5 minus 0.7 volt is 4.3 volt. So here also you can see the meter is showing you 4.3 volt across the resistor R. Okay. So here now if you want to find the total current, then the current according to Ohm's law, as we have seen earlier also, a current has to be equal to voltage, effective voltage upon resistance. Okay, so the effective voltage is how much? 4.3. It is 4.3 volt upon how much is our resistance? 1 kilo. 1 kilo means 1000 ohms. Okay, so this will come as 4.3 milliamperes as shown here. So it is 4.3 milliamperes. What is the current flowing? So IT, that is the current IT, is equal to 4.3 milliamperes, which is flowing here. So this IT is equal to 4.3 milliamperes. Okay. Then we'll go to the one more next problem. Example number 3. Determine the minimum average forward current rating that would be required for the diode shown. Now we want to know what should be the forward current IF. So here in the circuit we see that the applied voltage is 50 volt here. The main voltage applied is 50 volt. So because the positive terminal of the voltage is connected to anode of the diode, okay, so it is a negative to the ground, so it is forward bias. It is forward bias, and then you see a resistance, load resistance RL is equal to around 200 ohms, and you have to find out the current which is flowing in this circuit, which is called as forward current IF. Okay, now for IF to find out, we have to find out the effective voltage. Now effective voltage will be your this 50 volt, and the diode we will take it as a practical diode, so the opposing voltage what you have to overcome will be around 0.7 volt. So if you take the voltage, effective voltage will be 50 minus 0.7 volt. Okay, effective voltage. So that we will take here 50 minus 0.7 volt upon resistance, that is 200 ohms, which will give you 246.5 milliampere. So IF will be 246.5 milliampere. Therefore, the diode D1 must have an IO more than this. Now, this is for the basic thing, basic when the current will start flowing. Okay, but if you want the a diode to be a conducting, okay, then it should be more than 246.5 milliampere. Okay, therefore, the formula says that IO, okay, should be at least equal to 1.2 IF. So 1.2 multiplied by 246.5, which will get 295.8 milliampere minimum. So this is the minimum required average forward current, that is 295.8 milliampere. Then we'll go to the next problem. Then this problem is based on power dissipation. So example number 4, it says that calculate minimum forward power dissipating rating for any diode that would be used in the circuit. So here in the circuit we see that the applied voltage is around 10 volt here. So you have applied as 10 volt. This is positive, this is negative. So positive is connected to anode of the diode. That means the diode is forward bias, and then the voltage across the diode when it is forward bias, practically we can take it as 0.7 volt because it is the overcoming potential barrier. And here we see that the load resistance RL is around 100 ohms. Okay, now again we will find out the minimum forward current first, and then we will find out the power dissipation. So to find out the current, minimum forward current, the formula will be your Vs minus the potential barrier upon RL. So 10 minus 0.7 upon 100 ohms, which will give you, that is 10 minus 0.7 is 9.3 upon 100 ohms, which will give you 93 milliamperes. So that you can see here it is 93 milliamperes. Power is equal to IF into VF. Okay, so IF into VF. So IF is 93 milliampere, and VF, that is the forward voltage, which was the potential barrier overcoming, that is 0.7. That if you multiply, you will get 65.1 milliwatts. Okay, now this is the exact value, and according to the formula, the minimum power required is, it should be multiplied by 1.2. Okay, so 1.2 into 65.1 is 78.12 milliwatts. Minimum forward power is required. Okay, and then we'll go to the next problem, that is example number 5. So here it is example number 5 what we will take. Okay, so here in this example, he has asked an AC voltage of peak value 20 volt is connected in series with a silicon diode and a load resistance of 500 ohms. If the forward resistance of the diode is 10 ohms, find number 1, peak current through the diode, number 2, peak output voltage. What will be these values if the diode is assumed to be ideal also? That also you can find out. Okay, now here if you see the peak input voltage is around 20 volt, which is given in the data. So here you can see it is 20 volt, which is given in the data. Forward resistance is of 10 ohms. Then load resistance is of 500 ohms. Potential barrier is of 0.7 volt. Okay. The diode will conduct during the positive half cycle of an AC input voltage only. So here you can see the circuit. This is your diode. This is diode, and this is the AC applied. So diode will conduct when the input is positive half cycle. When the input is negative half cycle, it is not going to conduct, because when the input is positive half cycle, the anode of the diode will be positive with respect to cathode, and it will start conducting. That means when the input is positive half cycle, it will conduct. When the input is negative half cycle, it will not conduct. If you see the equivalent circuit here, then you can see this is the source, that is alternating source. So whenever the input is positive half cycle, that is positive half cycle, then the voltage across the diode will be 0.7 volt, and the resistance, forward resistance of the diode is 10 ohms, and the load resistance is 500 ohms. Okay. So this all we have to consider to calculate the peak current through the diode, peak output voltage. Okay. So here if you see, the peak current through the diode will occur at an instant when the input voltage reaches positive peak. So here you can see it is V in is equal to Vf is equal to 20 volt. Okay. Then Vf is equal to 20 plus If peak into Rf plus RL. That is If peak is equal to Vf minus V naught upon Rf plus RL. So it is 20 minus 0.7. So the applied voltage minus the potential barrier. We have to take this. The applied voltage minus potential barrier. This will be the effective voltage upon what is the resistance, the forward resistance plus the load resistance. So 10 plus 500. Okay. So this will come as 19.3 voltage upon 510 ohms. And then here you see the peak current, IF peak, will be equal to 37.8 milliampere. Okay. Then the peak output voltage, how much it is? Then the peak output voltage is the current whatever you have got multiplied by the load resistance. So current whatever you have got is 37.8 milliampere, and the load resistance is 500. So the peak output voltage will be 18.9 volt. Okay. Now, if you want to know the ideal values of peak current and peak voltage, so if you take ideal diode, then the voltage across the diode, whatever was there, V naught will be equal to 0 volt, because in ideal case we will see that the voltage is short and 0.7 will not take. And now in that case your current IF peak will be your voltage, which is 20 volt minus 0 volt upon the resistance also RF, that is the forward resistance will not take, will take only the load resistance, that is 500 ohm, because RF, that is the forward resistance, will be 0. That means this equation will become 20 upon 500. So 20 upon 500. So if you take this, it will become 1 upon 25. 1 upon 25. This is nothing but you will get as 40 milliampere. The current will be 40 milliampere. So here in a practical diode, we saw the current was 37.8, but for ideal diode, it will be around 40 milliampere. Similarly, if you go to see the voltage, peak voltage will be equal to IF into RL. So this will be equal to 40 multiplied by 500. Okay. So this will be nothing but 20 volt. This will be nothing but 20 volt. So here practically we got 18.9 volt, but here ideally we will get it as 20 volt voltage, and the current was 40 milliamperes. Okay. Thank you, students.